If you're just watching this video after I streamed, check out the description below for links to where all of the stuff is. This is a big, long video, lots of topics. So if you're watching this after the fact, check down there to find what you are interested in. It's going to be about, and the cat gets up. It's going to be about 10 minutes or 7 minutes before we get going on everything. And in fact, I'm going to let the cat out of the room. She doesn't like it when I talk. That's why I started with the cat cam anyway. So say hi in the chats for me as we get going. And if you're watching this later, check the description down below to skip right to where we're going to start. You want to go out, man? Go, 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 go. Are you going to get back in bed? I don't want you to bug me later. Hey Brandon, hi Chris, hi Jennifer, hi Disobey the Pope. Yeah, this is Spook here. He's loving the sun today. If anybody could type in the text or in the Twitch chat, that would be awesome too. Nice, and the tweet went out. Good morning, unexpected maker. All right, let me switch to this. Oh, it's frozen. Trying to use the overhead today. There we go. Let's do this. Is that what I want? And lock. Hello. Hi, Bruce. Hi, Grogard. Hi, M. Beelchris. Hi, Grogard. Thanks for joining. Hi, Anecdata. Hi, Charles. Oh no, the object thing's still happening. I was hoping it was fixed. I'll try to keep that reloaded. Hi, Javier. Hi, Ingo. Good evening from Germany. Thanks for joining. I'm hoping we can have lots of folks join in. I think it should be very exciting. Hi, Command, aka Nits. Sorry that the Discord chat is objectifying you folks. Hi, microDev. We'll get going in about 4 minutes. For those of you who haven't watched deep dives before, they are about 2 hours or so long. So it's gonna be a deep dive. I'll tell you that right now. It's gonna be exciting. I haven't found any videos on YouTube of people going into the details of the Rp2040 yet. So I'm hoping this video can be that for people. I'm one of those weird folks that is like totally okay watching like, I'm totally okay watching a 2 hour long video if it goes into super detailed stuff. Hi, Quarky. Oh, I'm glad you're catching it live. And Chris, sorry it's late. It's kind of impossible to pick a time that works for everyone. So I pick a time that works for me. Hi, Jim. Hi, Gary. I think I said hi to Gary. Grogard says, I haven't bought a Pico yet, but I definitely want to get one at some point. I'm interested mostly in the PIO stuff. Yes. That's why you should pick it up. And I'll go over all. Yeah, I'll go over all of it. I do want to just give some folks some time to join in. But I'll take questions as well. I'll take questions as well. Let me I'll pull up the data sheet while I can do that on the stream too. Retrograde Puppy says, will this replace my teensy for arcade button inputs? I need a USB controller to program for my fight box that's not $20 for a teensy. Yeah, you should be able to do like button monitoring to USB. Yeah, you should be able to do that. It won't replace something like a teensy 4 because a teensy 4 is just like super powerful. But for something that's just monitoring, inputs and acting like a keyboard or a mouse, like it's totally doable. Keith the EE says, hello all, hope the day's going well. Oh, let me tell you before we get going, I'm having a great week. I live in the US, so we got a new president on Wednesday. I've been working on this Rp2040 stuff for like a month now, and so it's very excited to be able to talk about it. The launch was kind of the end. Yeah. Gareth says the missing item from your year-end summary. Yep. And I've been trying to get, this is the exciting thing that happened today. I've been trying to get a AMD Ryzen 5950X to be able to like compile CircuitPython really quick. And I managed to snag one this morning. So I'm just like, it's been a great week. And I slept well last night. I didn't sleep well the 2 nights before because of the inauguration and the Pico launch, which was at 11 p.m. for me. But yeah, I slept well last night. The Rp2040 launch is going well, I think. So, Breton says, saw that Ren guys post 2 salvaging chips from the Rp2040 via hot air even before launch day is quite some dedication. Yeah, the Ren guy works for Raspberry Pi. So they probably didn't actually need to take a chip off. Hi, Phil. Hi, Parallel Logic. Who did I say? Not say. Hi, Dave. I don't think I said. And Gareth. Hi, Johnny. Hoping we're going to have lots of folks in here. And is anybody watching on Twitch? I don't see any. I have that window open too. It's just not on the video. Foamy Guy says, for folks in other time zones, I'm starting up CircuitPython programming streams and looking at Saturday mornings US Central Time, which may line up at a nicer time for some folks. I will likely stay more in Python and library land than core and C than Scott, but similar content in other ways. Awesome. Thank you, David, for the Twitch stuff. And Keith, thank you as well. Hi, Niradoc. I think there are a couple... if I miss a question, I think there's going to be a lot of people asking questions. So if I just forget one, just let me know, and I'd be happy to. I'm happy to answer questions. Okay, let's get going. I'll take a time code in the note stock here, and yeah. If you have questions, you can also drop them in the note stock, so I don't forget them. But we'll go into all of it. So. Let me start with housekeeping and take a time code. So hello. Oh wait, let me switch cameras. Since I'm going to talk to it. Hello everybody. My name is Scott, and I go by TanNewt online. I'm paid to work on CircuitPython by Adafruit. If you don't know what those two things are, CircuitPython is an embedded version of Python designed for microcontrollers. And CircuitPython in particular is designed to be very easy to get going, quick to program, and very fast to iterate on. We have a broad set of libraries that work across a lot of different microcontrollers under the hood. It means your code is super portable. Adafruit is an open source hardware and software company based out of New York City. And they do a lot of great work. So if you want to support me, you can do that by supporting Adafruit by going to adafruit.com. That is, they pay me to do this stream and develop CircuitPython. So support Adafruit, adafruit.com. Thanks to that. If you want to chat with me when we're not streaming or other folks get help with CircuitPython, talk about the Rp2040, the Pico, Adafruit does have a Discord server, which everybody is welcome to join by going to adafru.it/discord. the server's growing and growing, and there's all of the CircuitPython development discussion happens there as well. So if you want to follow along, check that out. This is a deep dive. I've been doing it for I don't know how long, maybe 6 months since the pandemic started. I started it around the ESP32S2, but we've got this exciting new Rp2040 chip. What they are is I do them this time normally, which is 2 p.m. Pacific on Fridays. I'm in Seattle, so Pacific time is kind of what my brain thinks of. It typically goes for 2 hours or more. I have a feeling we're going to have a lot to talk about today. So maybe we'll go a little over. We'll see. Questions are welcome. So if you have questions, just drop them in the chats and I'll try to see them. If it does scroll off, especially today, I'm expecting lots of folks and lots of questions. Just go ahead and post it again in case I miss it. Next week is Friday normal as well. The last piece of housekeeping is that you can see the cat in the cat cam there. His name is Spook. He's epileptic. He does have seizures from time to time, although his new meds have been working really well. So that probably won't happen. But if I'm like on the stream without like talking at all, it's because I'm making sure that he's okay. And I'll mute and do that and do that. So that's it for housekeeping. Let's continue. Looks like my timer is just a few seconds too quick, but that's okay. So this deep dive, we're going to talk all about the Rp2040 and the Raspberry Pi Pico. Let me switch to the overhead. So this is a Pico that I was sent by the Raspberry Pi folks. So thank you to the Raspberry Pi folks for sending me this Pico. They sent it to me about a month ago. I was lucky enough to hear first rumor of it from Lady Ada, and then from Lady Ada, and then she asked the Raspberry Pi folks to include me so that we could get a jump on it. So yeah, I've had lots of times to read over the datasheet. I've done some development in bringing CircuitPython to it. So I'm hoping that we can get in the weeds and talk about the details of the chip. What I should say is that there's actually two really interesting things in the overhead here. The chip itself is dubbed the RP for Raspberry Pi 2040. And then the board itself is called the Raspberry Pi Pico. And I think that's something we need to be clear about, is that this is actually two things, and it's very exciting for the fact that Raspberry Pi is designing their own silicon and getting it manufactured. And then it's also interesting that this board is interesting, the Raspberry Pi Pico, because it's really inexpensive. They're giving it away with all of the Hackspace magazines this month. And they're also, and it's like $4 US. So, and there's a lot. They made a lot of the initial run. So if you haven't bought one yet and you want to, I kind of bet it's still going to sell out. But there is a lot of stock initially, so you should be able to get one now if you want to. So yeah, this is the Raspberry Pi Pico. It has the Rp2040 on it. We'll go into details, technical details in just a bit. I'll pull up the data sheet. I do want to, since I have the overhead up here, before I go to the desktop. Hi Juan, thanks for making it. And Mark, sorry there's no closed captions. I think I'm on the right settings for YouTube that it should have been there. But yeah, so what we have here is Timon says, so far it's all pre-orders, what the shops listed yesterday. So what they released right now is just the Pico board. The chip itself is not available more broadly. So what I have here is a prototype Adafruit Feather Rp2040. So this is a Feather form factor board, but the microcontroller on here is the Rp2040 as well. And this design is basically all set to go. This design here is not the revision that we will launch with. There's one pin change that we did, and we could talk about that. But we'll basically have these once we get the chips from Raspberry Pi. And they said in their announcement that the chips themselves will be available in the second quarter. So I'm not sure when Adafruit will get them, but we're basically, I think, ready to make them when we get them. So yeah, this is coming, and I've actually done more development on the Feather than I have on the Pico, and we can talk about that. So let me just check the chat. Pico was pre-ordered in every shop, but shipping date was like 28, so soon. Yeah. I know Adafruit, we put them in stock and they've shipped out. Like all of these here, this is actually an Adafruit order I got this morning. Nerodoc says at least you get a reset button on the Feather. Yes, that's true. And I know we have a lot, but I don't think they were putting them all in the... Are there more than one Pico live stream? If you have, let me know if other folks are streaming the Pico. I'm curious. Okay, let me switch to the desktop here. Do we want to talk specs, or one thing I definitely want to do in the stream is, oh, Hackster is streaming now. Thank you. I didn't realize they were. We'll have to check that out. I'll check the recording out after this. Okay, so do we want to talk specs, or should I actually show how to use it? Actually, let me just do that right now, since I have the overhead up here. So what I thought I would do is basically show in the next minute how to get CircuitPython on it. A couple things. This is everything I got in my order. So I got a number of Picos, and I also got my Oshpark order. I thought I'd just mention this. This is the thing that I was going to use to get the power like through a USB connection to the Nordic PPK2. Gareth says, don't read the specs, turn it on. Okay, yeah, we'll do that. I also got another Raspberry Pi module because I do want to get CircuitPython on that. Somebody made a comment yesterday. It was like, this isn't what you meant by getting CircuitPython running on a Raspberry Pi, is it? And I was like, no, but I'll do it. I picked up the new like capacitive touch breakout thing. I got one of the nunchuck adapters because I think I have nunchucks around here somewhere, which is cool. Looks like AT Makers picked some up at Micro Center, so that's cool. And okay, so I got 3. This is the limit, I think, for this is the customer limit. And this is, I think it's important to note, I believe, like some folks have been talking about the way that the Pi Zero was limited. And I don't think these are the same. You should be able to see that once these become regularly available, you should be able to buy a lot at the $4 price point. So let's take one of these out and show how it works. So I'm just going to cut it open. It doesn't come with headers. You can buy from Adafruit a version for $5 that has loose headers that you would have to solder on. The one that I have that has headers is actually that the Pi folks sent it to me with. Gregory says, could CircuitPython be implemented on the Raspberry Pi 3 and 4 through emulation? You don't actually need to use emulation. You could do the drivers, or you can use a lot of the drivers for CircuitPython just in CPython via the Blinka library. But I would actually like to get CircuitPython running bare metal on the Raspberry Pi as well, meaning no Linux underneath it. Who's soldering the headers? Human or machine? I mean, the headers I got were probably human soldered. Okay, so this is... Oh, and it froze again. All right, let's switch to the desktop. You can see in the frozen image, the most important thing to see in the image before we switch is that there is one button on this board. It's the white button there, and it's called Boot Select. So what I'm going to do is I'll just tell you and switch to... And of course, I didn't take a time code. Let me take a time code. Desktop. Make this smaller so you can't see it. And I'm going to pull up here. So I'm not actually sure. I haven't done this with a fresh one, so we'll see what happens. I have a, or I know what should happen here. So here's my file explorer, and what I'm doing is, you can't see it. Anyway, I'm holding the boot select button and I'm plugging it into a USB micro cable. And then you can let go of the button once it's plugged in. And just like CircuitPython does, it shows up as an Rp2pio. And if you click onto here, it mounts and there's info about UF2. One thing that's really cool about this is that this UF2 bootloader, unlike all of the other ones we have at Adafruit, this one's in ROM, which means you cannot erase it. It will always be there and it will always work, which is really, really cool. It's the first board to have UF2 built in, which is really epic. So next step, what you're going to want to do if you want CircuitPython is you could go to this page. It's circuitpython.org/board/Raspberry Pico. And we just released 6.20 beta 0 earlier today. And this is the first pre-release. It's not even factory flash tuned. It's in the ROM. It's in the ROM. So yeah, like, yeah, it's not just written there. So I'm going to click download UF2, and it downloaded here. And if I just open it up, here's my downloads folder that has lots of stuff, but this is the file I just downloaded. And so I'm going to drag this 6.2 UF2 to the disk drive and copy it. And it's copying over. And once it's done, ROM is not, Ren hinted at that bit. Interesting. If it's factory flashed. I don't know how it's implemented. Ren would know. Okay, so CircuitPy drive showed up, and let's see what it does. So now we have CircuitPy, and if you've used CircuitPython, you're golden. This works the same way as before. So if I, let me double click code.py, and code.py here is just a print hello world. This is our standard code.py that we do when we create the file system. And if I want to connect to it, I'm on Linux. This works on Mac as well. You can do screen. And then I have a second CircuitPython board connected, which might be the timer. Let me just be a little bit careful because I don't want to mess the time up. SDC. Where does it tell me? ACM2, okay. I was about to Control-C it, but that would lose the time code. Les says I was using CircuitPython on the Pico yesterday at work. It works great. Awesome, thank you. Yeah, I've been working hard on it. Okay, so if you connect to it and you don't see anything, what you can do is you hit Control-C, and that will get you this prompt. So we can see here that we're running the 6.20 beta 0. And that is for the Raspberry Pi Pico with the Rp2040. So now this is what's called the REPL, which is the read eval print loop, where you can do things like just type in 1 + 2 and you get 3. You can say print hello, and it just does it immediately, which is really cool. I also like it for seeing like what APIs are. So you can do import board and then dir board, which will list all of the things that are like attributes on the object. So here you can see all the different pin names. Really helpful. But the problem with the REPL that I don't really recommend, folks, is that it is ephemeral, meaning the code that you type in here doesn't get saved anywhere. So it's great for figuring out what pin name do I need. But it's not great to like iterate and develop on code. So what you do is you hit Control-D, and then here you can see that it actually ran our code.py with hello world. So now if I scooch this over to the side and make this window smaller, I'll show you how to edit. So in CircuitPython, on the Rp2040, generally, we make it really easy to iterate. So if I want to do, I could just say hello Pico and hit Control S to save. And now it reran the code for me and did hello Pico. I can do that again and say for I in range 10. We can do 10 hello Picos and just hit save again. And now we get 10 hello Picos. So that is the very basics of CircuitPython. I don't want to cover kind of like all of the basics because frankly, we have really good documentation and this is a deep dive. So at this point, I think we should go to the datasheet and then we can talk about questions as well. Chris asks, any idea on TinyGo support? I don't. I work on CircuitPython. I haven't seen any mention of that. I did hear a rumor of Rust support, and I would expect that that happens as well. Yeah, Toddbot says, let me take this moment to vote for being able to disable specific USB devices in CircuitPython. Yeah, that is on our list. You can check out the CircuitPython issues for all of that. Okay, so let's do a datasheet overview. So there's some really good resources if you want to know more about the Raspberry Pi or the Rp2040 and the Pico. Paul says, hey, late to the party, did someone release a new board or something? Yes, somebody not only released a new board, but Raspberry Pi designed their own chip and released that as well. David says, can you choose the core used to run CircuitPython? You cannot. It just runs on the first one. It runs on core 0, I believe. There's some code that like we're built on the Pico SDK, and so the Pico SDK kind of manages the startup stuff. So there's a blog post from yesterday that is a good resource from the Raspberry Pi folks. There is a Hackspace magazine, which you can get the digital copy. I was reading this earlier. It covers a lot of the same things, but it does also give a little bit of background on like how long they've been working on it. I thought it was interesting that it's like a 40 nanometer process because I'm kind of a nerd like that. That is kind of a gauge for like how big transistors are. So like I said I just bought a new Ryzen, and the new Ryzens are on a 7 nanometer process. So that can kind of like give you an idea. Two folks are asking about the cores. So for those of you who haven't been following along, the best resource, I thought I had this open here, but I don't. Oh, it's just not. So the best resource is this Pico Getting Started. And I think that's right. Am I in the wrong spot? Pico, more info. Products. View documentation. Getting started. Board specs. I want the datasheet. Okay, it's downloading. I wanted to download it again because I might have had a pre-copy. So here's the Raspberry Pi 240 datasheet. Thank you, Todd, for the link as well. This is the first thing, and I've seen a lot of people saying like why this chip is so awesome, is these docks are awesome. That was like when we were debating like whether we should put effort into this chip, I took a look at the docs and I was like, yeah, we should take a look at that. Juan says 40 nanometers sounds large, but how does that compare to other MCUs? I don't actually know. I haven't heard what the others are. I think it's pretty comparable. I suspect it's comparable because the really small nanometer stuff is just like really expensive still. Like the 7 nanometers, like a really expensive process. Yeah. So like, there's a data sheet. There's a data sheet for the Pico, the board. There's a data sheet for like hardware stuff. Nice. And Lady Ada is in the chat as well. See if you have questions for her as well. Corky points out that nanometer designations are a bit foundry dependent unless they use TSMC. They do not use TSMC. That's one thing they cover in the magazine. They do Sony Tanazawa or something. One thing I liked about the datasheet, and maybe we should cover. Let's cover the high level stuff first, which is usually in the introduction. I like these tabs, but it takes so much space up. So we'll close those. So here's the key features. Let's just briefly go over these so that we're on the same page. Tom's Hardware reported they were using TSMC. Check the Hackspace magazine. I think it's in there. Unexpected Maker says ESP32 is TSMC's 40 nanometer. Maybe I'm wrong. Okay, so dual ARM Cortex M0s up to 133 megahertz. I believe that the core, I know the core clock rate is 125 megahertz, and that's currently what CircuitPython is clocked at. There is 264 kilobytes of on-chip SRAM in 6 independent banks. And the way that's broken down is it's 4 banks of 64K, which gives you 256K. And then there's 2 other banks that are kind of like scratch RAMs that are 4K apiece for a total of 264. I think there's also, there's dedicated RAM for USB, and there's also dedicated cache RAM for the flash. And that gets to this point, which is there's actually no onboard flash. Okay, so now that we've confirmed there's 2 cores, Mark says, sorry if this was covered before I showed up, but can CircuitPython use both cores or not yet? The answer is not yet. Micropython has it so that you can do, you can use the thread API in Micropython to use the second core. But I'm kind of like not exactly sure the way that we should expose it in CircuitPython. So hold that thought. We could talk about it. And threading is like one way we could do it. But I've been thinking more. The crazy idea I have is that Python's role in my mind is that, yes, and Timon is getting to this too. It says, can you program the cores separately? For example, run C code that can talk to CircuitPython on the second core. And microDev says we want all the cores. So the question is, what do you want the second core for? And I'm thinking more like Timon says, and Luke, who worked on this, also says you could run some DVI on the second core. Yes. So I think that I think it's more interesting actually to not run Python on the second core. I think Python's role in microcontrollers in general is to orchestrate and iterate, it's orchestrating separate things that are doing stuff easily, right? Like the whole point of CircuitPython is like you can iterate really quickly, but then it handles all of the timing sensitive stuff for you. And there's a lot of ways we can do that on this chip, which is why it's really interesting. And so let's keep going down. Let's keep going down. Todd says I'm going to run basic on the second core. You can, although there's basic Python that I sketched out. Mark says run 2 copies of CircuitPython at once for reasons. I think you'd want threading. Like there's like you need something that shares across the 2. Can you invoke inline assembly from CircuitPython? No, but we can talk. We can talk. So many questions. Yeah. So Juan says, can you sleep the second core to save power? Yeah. The startup code should put the second core in just a wait for event loop. So it's just waiting. But yeah, one core is like concurrency is really hard. You all are on the same page as me. So let's keep going down here so that we can talk about why I'm thinking that CircuitPython shouldn't run on the second core. Okay, so there's DMA controller, which is great. Fully connected AHB crossbar means that like all the things that may need to read data or read memory can do that on their own. Luke confirms that the second core is left in wait for event plus deep sleep. So yeah, it should be basically as off as it can get. Okay, there's interpolator and integer divider peripherals. This just like accelerates the number crunching on the core, I think. I haven't played around with that. There's an on-chip programmable LDO to generate the core voltage. So you give it 3.3 volts, but the core, I think, is 1.1. And it's done all internal to the chip, and the SDK sets it up for you, so you don't have to worry about it. 2 on-chip PLLs that take the external oscillator and create the USB speed and the core clock. There's 30 GPIO pins, 4 of which can be used as analog inputs. And the cool thing about this also is that these do not that 30 number doesn't include the QSPI pins, the SWD pins, or the USB pins, which is really, really cool. So you actually get 30 to play around with. Skazi asks, can I use any quad... I should be taking time codes here. I'm sorry, I gotta slow down a little bit. Oh, somebody's doing it for me. Thank you. I suspect that's David. So, So the question is can I use any quad SPI memory with Rp2040 like an MRAM memory? Does UF2 support these memories or only flash memory? I don't know. And so what you have a chance to is that the initialization code, the initialization code for it is loaded off the memory itself. So there's some like basic commands that you do have to respond to, and for it to load that 256 bytes of code that is used to initialize the thing. It's run by the SSI peripheral here. That the docs are really good. Just look at the docs and it'll tell you like your chip must support these commands. And command says that as well. So check out the docs for that. I don't see a reason why not, but I've never used an MRAM chip, so I'm not sure whether the command set overlaps or not. Okay, let's keep going. 2 UARTs, 2 SPI controllers, 2 I2C controllers, 16 PWM channels, where it's 8 slices with 2 channels apiece. And in CircuitPython land, that means that each channel shares a kind of a base frequency. So you can have like 2 things going the same frequency with different duty cycles. Yeah, some people in Twitter are really like being a bit harsh on this, and I don't think that's warranted at all. And I'll tell you why after I read these like last 2 points. It has built-in USB with host and device support built in PHY, and also it has 8 PIO state machines. So PIO is kind of like the thing that they're most excited about. Charles says the Pico has 2 megabytes of flash. Can it handle larger flash chips? Yes, it can handle up to 16 megabytes. Yeah, so the PIO is short for Programmable IO. And they're really interesting because we talked about this last week on the deep dive, which is what is real time? Because I was saying like CircuitPython is not real time, and real time is like also relative to like how real time you need things to be. And the PIO state machines are almost CPU processors that are like a custom instruction set that make it easy to do real-time communication kind of to the outside world. And then that, and so they're programmable. And so they're just like super interesting because they're basically, this is a dual Cortex M0, but there's also 8 of these state machine cores that are like almost but not quite like a full CPU on its own. But they're designed to be very good for real-time stuff, which is really cool. Mr. Who 30 says CircuitPython has a list of supported flash chips in the source code, which is easy to find. Yes, I'm not sure all of those will work, but they are. There's one other requirement that I want to have for. This is so good. So many folks. It's awesome. Let's get into PIO in just a second. Let me just address the flash chip thing. One of the constraints that I did find for flash chips is, sorry, I think David, who's helping me out with timecodes. One of the constraints CircuitPython is going to have for the flash chip is that we have no unique ID, which is what we use for serial number in USB. So the flash chips, most flash chips have a unique ID on them. And so our plan is to just use that. So that'll be an additional constraint that we'll have for CircuitPython. So we'd really like to be able to get a unique ID from the flash. Okay, so let's talk PIO. And let's just go into the datasheet. So again, like the Raspberry Pi folks made amazing docs. So if I don't cover everything here, check out the docs. They've done a really nice job. I recommend, if your PDF viewer does not have a table of contents, find one that does. It makes it really good. Oh, Juan Carlos points out CircuitPython has 1,999 people have started CircuitPython. So if you have not started CircuitPython on GitHub, please do. It's github.com/Adafruit/CircuitPython. We'll break 2,000 today, which would be really cool. So yeah, as Bruce says, start starring. Okay, let's just jump to the PIO because that's the most interesting. It is accessible. So there's already Micropython support for the Rp2040 as well. It's official. Raspberry Pi paid for it. So you can use it there. And we have the beginnings of support in CircuitPython, but we haven't just copied. We haven't just copied it. And we can go into the why my API for PIO is different as well. But let's just talk about PIO because I think that's what folks. I mean, it's probably the most interesting part of this chip. Let's be real. So let's take a look at this diagram. Okay, so there are two. So PIO is short for Programmable IO. There are 2 in the Rp2040, and each of those in the Rp2040 has 4 state machines. Yeah, the G is silent. They have 4 state machines, which are things that run instructions, but the instructions are not as comprehensive as you would see even on a Cortex M0. But they run those instructions independently of everything else, which makes them really interesting for stuff. So if we look here, so there's only 2. The state machines are almost independent. There's 2 things that they share. They share IRQ lines. So IRQ is short for interrupt request. This is a way that you can cause the main CPU, either one of them, to basically stop what it's doing and do something else. So that's what an interrupt is. And the state machines themselves can read the state of the interrupts too. So interrupt state is the only way to communicate between. It's not, I guess you don't necessarily, that's not the only way you could communicate, but it's like the primary way I think you would communicate between state machines. David asks, are the state machines running at core speed? So yes, they can run up to the core speed, but each state machine has an independent divisor as well. James is comparing this to the PRU, which is the name, I think, in the BeagleBone. I've not used that, so I can't like do an apples to apples comparison. Bart says, what is an example? So any sort of protocol that is timing sensitive is what the PIO is really useful for. The classic maker example is NeoPixel, where NeoPixel is an 800 kilohertz signal. If you are transmitting a 0, you do a third. Yeah, Distribu says NeoPixels. If you're transmitting a 0, you do a third of that 800 pixel cycle. And if you're transmitting a 1, you do 2/3. And we can get into the weeds about this. That's an example. CircuitPython, if you download 6.2 beta 0, already uses PIO to do it. In comparison, for the SAMD21, what we have to do is we have to we bit bang it, which means that you use a CPU core to transmit the data instead. And we actually have to turn off interrupts so that we know exactly what the timing will be from the core. And that gets really hard. You can post Micropython stuff. Just know that the APIs will be different for PIO between Micropython and CircuitPython. One of the reasons that it's different is because Micropython allows you to pick which PIO it's on, whereas CircuitPython will not allow you to do that. And the reason that it's not going to allow you to do that is because we use the PIO internally as well. So we actually need CircuitPython to manage, like, okay, you want this state machine, you need a state machine, here's one, and your program's this size, here's one, that sort of thing. Okay, so for state machines, the other resource that they share is this instruction memory, which is 32 instructions. It's not a whole lot, but the NeoPixel example is only 4 instructions. So there is a lot of room to play. Each instruction, which I'll scroll down and we'll talk about in a bit, is pretty powerful. So it's pretty like dense. Timon says, oh, and why does CircuitPython need to use the PIO? Well, 1, NeoPixel, and 2, things like we already have an I2S API. We already have like a, yeah, we have I2S. Like we have some APIs that we will implement with PIO. So we need that flexibility. And Luke, who's in the chat, who worked on this chip, says 32 instructions unless you use out exec. So there's 2 ways you can run instructions that are not stored in this memory. One is if your instruction is out exec, it will get it from the FIFO, which I should talk about. Or you can write from like from the Cortex M0, you can say like, just run this instruction by writing to a register. And it'll run that as well. Kuzatuna says it'll help with timing sensitive sensors like the BNO 055. I think the BNO 055 is still, it's still I2C. I think it's just like a little weird with that. Will you implement CAN bus with PIO? I imagine it's possible, but I have not seen an example of it. You'll still need a transceiver, I assume. But yeah, I assume it's possible. So let me go over some more of this. Okay, so we talked about interrupts being a shared resource, and we talked about instruction memory being a shared resource. So what is not shared? So each of these individual state machines has a FIFO, which is short for first in, first out. And each one is 4 32-bit words long. And there's one going in and there's one going out. And the benefit of a FIFO is that it can, it makes communicating with the state machine less timing sensitive. So if we're talking NeoPixels, right, and we're transferring, say, just a byte at a time, we can write 3 bytes and then the state machine will chew through those bits as it needs it. It gives us some, like, in the docs, they call it slop. So it's timing slop. So like the Cortex-M0 can like queue up some stuff, although we don't use the Cortex-M0 because you can use DMA. It just like, it gives you some wiggle room in terms of like getting things synchronized together. So FIFOs are really handy for that. So there's a FIFO for each state machine, which again is independent. And then the state machines themselves can talk to the GPIO. They can talk to any of the GPIO. We can talk about how that is. It can also talk to whether the output is enabled or not. And then input-wise, I think it always gets the input. Yeah, so that's the super high level. Here's some examples. So it can do like 8080 and 6800 parallel bus. So that's like DisplayIO parallel bus is what they're talking about. I2C, although CircuitPython won't use it for I2C currently. We use the regular I2C ones. 3-pin I2S, which we're going to implement. We just haven't yet. SDIO we haven't implemented, but that's like the faster way to talk to SD cards. SPI, DSPI, dual SPI, and quad SPI, we don't have that implemented, but you could do it. The SPI in CircuitPython is just using the other SPI peripheral. Generally, like, those are less interesting to me because I'd rather like save the PIOs for the things that only the PIOs can do. So Timon says, I was wondering about that as the docs mentioned these PIO1 and PIO2 peripherals, which sounded like only 2 pins would be usable via the PIO. So what Timon is talking about is the pin GPIO functions. So there's a mux that like the outside world basically is called a pad. And that's the thing that like drives enough current and circuitry to actually send the signals out of the chip. And then internally it's like a lot lower like power signals. So like the pad is the thing at the very outside, and then there's a GPIO mux. I talked about this a little bit last week. And it decides who kind of gets control of that pad. And so the reason that there's a PIO0 and a PIO1 is that only one of the PIO peripherals, again, like each one has 4 state machines, but you can't have a pin being written by 2 at the same time because of this. So if you had a protocol that like multiple state machines need to reference the same pin, then what you would have to do is you would have to make sure they're on the same PIO. And there is a process for if you have 2 state machines that are asserting different values, there's a way that like it negotiates which one wins. Yeah, Nerodoc says, what I understand is that the pins have to be grouped in a certain way, which is replicated on the feather for that reason. I'll get to that. And that was something that I requested from Limor. Again, I'm not going to be able to read the whole docs, so let's keep going on PIO because I think obviously people are excited about that. There's a question for Luke in the chat about the USB lines on the Pi Pico. And yeah, like Breton says, I would guess that it doesn't matter because USB 1.1 is not that fast. Okay, so there are other resources. I think there's a diagram here. Yeah, so here's an example of a state machine, a diagram of the state machine. So we talked about the FIFO. So there's a TX FIFO and RX FIFO. And there's also, so there's 2 registers. If you've played Shenzhen IO, it's kind of like that. Shenzhen IO is like a game where you have to like do very limited programming based on like just a few registers. So registers you can think of as like memory that are kind of like isolated and only accessible from the code on the state machine. So let's see, there's an outshift register, which you'll see abbreviated as OSR. There is an in-shift register, which you'll see as ISR. And then there's a scratch X, scratch Y. Each state machine has its own clock divisor. which means they can run at different speeds. Toddbot asks, are there some examples doing USB host on the Pico? I believe there is an example in the C SDK. Are USB micro connectors heaps more cheaper than the USB-C? Wondering why they went with the older micro. You'd have to ask them. The Feather does have USB-C on it. So if you want USB-C, there will be options for sure. Okay, so there's PC, which is the program counter, which you can read. And that's going to range between 0 and 31 because there's a 32 instruction memory. And then there's control logic. And that control logic can talk to and from GPIO and IRQ interrupt stuff. Toddbot says USB-C connectors are still twice as expensive as micro USB. Okay, so let's talk about the instructions. Let's not talk about the example. Does that make sense? We could even do some demos here. We've got time. So here's another interesting diagram for the output shift register. I guess let's just talk about, I want to just talk about okay, so let's start here. Can everybody come to the Discord chat rather than the YouTube chat? Okay. So there are, let's go here. There are 9 instructions. I think it's 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So there's jump, wait, in, out, push, pull, move, IRQ for interrupt, and set. No, everyone come to YouTube chat. David asks, is it a fully Turing machine? In the docs, it says it's likely Turing complete. So it hasn't been proven. Okay, so what you'll see here is, so instructions are 16 bits long. And the first 3 bits kind of classify the instruction. Now, if you have 3 bits, it's weird that you have 9 instructions because 3 bits only encodes 8. But if you look closely, push and pull have the same top 3 bits. And bit 7 here is different. So let's just, let's see, where do I start? So if you're doing flow control, which is like, Mike says, is there a new Featherboard with the RP2040? There is, but it's coming soon. We don't have the chips to make it yet, but we'll sell it. It's designed. I have it on my desk. But yeah, so flow control, you have some options. Should I start with flow control? Or should I talk about how you get data out? Okay, so to get data in, there's an in instruction. And actually, let's just scroll down. I'm confused. It does so much. So all instructions can do some things. And that's what this common 5 bits here is. It's delay and side set. So delay allows you to add additional clock delay after an instruction runs. So one of the cool things that makes this really good for real time is that each instruction takes 1 clock cycle. However, that might be too fast for you. So you can have up to 5 bits of delay. So basically the way you can think about it is that it will run the instruction and then count down the delay. So if you have an instruction with a delay of 2, the instruction takes 1 cycle and the delay takes 2 more cycles. So if you're looking in your line of assembly, PIO assembly, you'll see 1 line, but it actually takes 3 cycles to do that 1 line. So delay is really handy for timing. And we can we got another hour, so we can do some examples to show that. But the important thing to note is there's also this note of side set. So side set is one of the 3 ways you can output data to a pin or somewhere else. Output data to a pin. So there's out, set, and side set. So side set is special because it can set a value concurrently with doing another sort of output. So that's what you can see here, is that also in and out can do side sets as well. So it saves you from the cases where you need to like set your clock high at the same time that you set your data high, for example. So that's what side set does. And you can have up to 5 wires that are set by side set. But note, it's delay/side set, which means for every bit of side set that you do, which I think is actually the top bit down, you lose resolution on how you can delay. So note that there's a trade-off there. And what you do is you'll tell the state machine like how many bits of side set it has, and it'll figure out how much of that is delay as well. So delay and side set are common to instructions, and then each other instruction has options. And we can go through those if people think that would be helpful. Yeah, maybe we'll just do a quick overview of that, because we could actually get to some examples here. I don't have everything set up, but we can do it on the fly. Pick an example. Yeah. Okay, let's do an example. Let's show how I want to do this in CircuitPython. Yeah, DCD says curious about CP examples as well. So let me just cover these. So let me just cover these generally so that you know we know what we're looking at. So JMP is short for jump. What this does is it allows you to, based on some condition or always, go to another address. Wait is another way to just delay, but you can also like wait for like external state. So like you can wait for a pin that you're reading in to go lower, for example. So in what it will do is it will read data from the pins or from the source and push any number of bits, that's what bit count is, into the input state register, input shift register. Out is the reverse, so it takes bits from the out register and puts them somewhere. There's also, so then what you have is push and pull. And so this is how you get data from the FIFOs, the TX FIFO into the output state register, or the RX from the input state register to the output to the input state register, shift register. It is complicated, but it makes it really powerful. Yeah, folks want to see an example here. So I will do that. And let me just talk about these last 3. So move allows you to move stuff from like the scratch register to input or output state shift registers. Interrupts allow you to set and read and wait for them. And then set is another way of setting values to another set of pins. Okay. Yeah. And Luke points out like there's really good docs about this. And so if you look in the STK example, there's examples there. But I think I want to live code this. And I have a Saliate on my desk that I'll climb under and I think it works. I think it works on this computer. Okay, so let's do an example, and I'm going to use the feather because frankly, the feather is a little bit easier to work with. Sorry to everybody who has a Pico, but actually I'll use the Pico. The Pico's got an LED. We can use that. We can use that until we need to scope it, which I'm going to want to do. I'm going to want to saliate it. Okay, I'm going to use the feather, and I'm going to have to redo the overhead here. So, overhead, frozen, unplug, replug. Where is it? There it is. I don't know why it stops. Overhead. Hover cam. Okay. Okay, so what I have here is the Rp2040. And I'm just going to plug it in. And you can see that the light is acting like the light would normally does for CircuitPython, which is good because that's using NeoPixel. And if I just look, oh, look, I've got two CircuitPys. One is the Pico. Okay, let me safely remove that one. Oh, and it's saying it's open, which is close. This is the one I want. Oh, look, I even have my test code on here. Okay, so let's open it up. What am I doing? Okay. So this is just a NeoPixel test. And you can't see it. I realize that now. Desktop with overhead. There we go. So what I should be able to do here is just edit. And it's yellow for 10 seconds, and then it should go back. And then I think what I also have, oh no, I don't have that set up. One thing I was doing is I was reading the potentiometer here that I have and making the brightness change. But none of this is PIO stuff, so let's rename it and pixel test. And then I'm going to rename this because the library is renamed. So the way that I want it to work in CircuitPython is what you do is you write PIO ASM and then you call assemble, and that produces oh, hey folks, they enabled more Picos in stock. So they put a few hundred in at a time. So if you didn't buy one from Adafruit and want to buy one from Adafruit, now's the time. Okay, so let's open this code.py. Oh, and it refreshed and then I didn't realize it. Don't need that. In fact, let's just close all of this stuff. Okay, so here's my test code. The library is available. So my idea is that what you'll do is you'll just write it in a string, or actually I should add the ability to load it from a file. But I think that people are going to share things as PIO ASM, and so I wanted to support that. So what you do is, this is just test timing stuff. So you take a program and you call assemble on it, and that will produce the like encoded version, bytes version. And then what you do is you say, I need a state machine, and this is different too. We'll have to fix this code. It might be using slightly older versions. But you give it the program, you give it the frequency, you give it an initialization program, and then you can tell it what pins you're using. So that's the way CircuitPython has it going. And then once the object is constructed, it's running. And then if you want to do something like NeoPixel, you just say state_machine.write, and that will write the data out to the state machine. This is where the like support is incomplete, and I've been thinking a lot about how to do it. Right now, we only have a way to write to the TX FIFO. I haven't added a read yet. I was kind of mimicking the way that SPI is working. But I don't know. I haven't decided that yet. There's some interesting things that we could do on how do you get data to and from Python, or from somewhere else, out to a state machine. Okay, so the other thing I want to set up is I want to show the Salier logic level analyzer stuff. So let me get that going. I just switched computers. Those of you who have followed me know that I've been like, oh yeah, I'm using my Mac. Well, the reason I was using my Mac was so I didn't accidentally leak the Rp2040 on this stream. I didn't want it like in my browser history. I didn't want it anywhere. Sorry if I'm getting set up here a little bit, but it's all for the best, I think. So I'm gonna take my headphones and I've got to plug this in under, which you can't see. Plug it in under my desk. Okay. Yeah, Bruce S says, when I worked on NDA stuff, I had random names for it all. Yeah, and Pico, like, if we just called everything Pico, it would be vague enough, I think. But I did not want to be the person to leak it. And I wasn't. So let's open Logic here. Hopefully it works. Falconhead is saying, can we please get bear chips in the store? And Lady 8 is like, we only have like 10. So. All right. New version. And this is not all the settings for. I'm just going to do one. And I think what I'll do is I'll do it on D13, which you can see. So D13 is interesting on the feather because it is the pin that's also the red LED. So this needs to go to ground, which is this pin as well. It's annoying. I think that's it. I'll take this out. We don't need that potentiometer. Okay, so I think what I want to do is I want to start with a square wave because it's just, I think, a really good place to start. So I'm going to use D13. Going to blink it and then turn it off, and then I'm going to do a square wave. And then I'm going to run it at 800 kilohertz. And I don't actually need side set. And autopull. I'm going to simplify it here. Right, so Gareth says, so you can reprogram the PIO dynamically if you wanted to. Once it's running, you can't reprogram the instructions. You'd have to turn it off to do that. Maybe not. Maybe you can write it. You can't read it. Freeze the overhead cam if there's another unannounced product coming soon. You're going to be... if it freezes, you're going to be sad because I don't know of anything. This was the big one. Okay. Luke says you can hot patch the instruction memory. The Hub 75 example does this. It's a bit of a hack. All right, so we're doing square wave. I've got this like prototype thing just to make sure that everything's set up. So let's invalid digital trigger settings. capture duration. Let's just do a second. So we're getting nothing until I save. And still nothing. Let's get the console open too. And this is on the wrong board. I still have the other Pico plugged in too. So let's. Okay, so I renamed it. This code's a little old. Gareth says, "Can you destroy and recreate a PIO scheme?" Yes. Yeah. So in CircuitPython, we track what you're using. So all of our CircuitPython objects, you can say Deinit, and it will release all the resources and allow you to reuse them later. We also Deinit everything when your code finishes to make sure that the next run of your code starts fresh. Graham says, "Init, nice idea. Thank you." Graham works at Raspberry Pi as well. Okay, so we renamed this Rp2pio. So I'm just going to have to Rp2pio and hit save. And the trigger didn't trigger. No module named PIO ASM, and that's because I renamed that one. Adafruit _ I wanted to leave the name in case somebody else named something that way. I'm hoping we see a trigger here. We should have. Did I? Oh, it's blinking. Did I plug in? I think I plugged in the right spot. Why isn't Celia? Oh, you know what? I'm not plugged into channel 12. That's the worst. I'm plugged into channel 4. Stop. Always check your channels. It's the same color. Okay, so if we hit start. Okay, we can see we're blinking. Yeah, that's what deep dives are all about, is like figuring out what the common mistakes are. Okay, so what we have here is we can see that we have a 50% duty cycle, we have a high, and we have a low. And if we look at the frequency, it's 1.2 megahertz. And you could think like, oh, that's like definitely not the 8 megahertz that we set in here, or the 8 kilohertz. But what we're actually doing is 800 kilohertz by 6. And if we look at this real frequency, you know, I wonder if I fix this. Let's load a new version. I had a bug around frequency at one point. So let's make sure we're using, let's if you want to see what version you're using, you can Control C and enter the REPL. And you can see I built this on January 14th. So this code's all a little old. So let me just Control A K, and then I will eject. Safely remove. It still thinks that one's open. I don't know why it thinks there's something open on it, but I'm just gonna yank it. Hopefully that's okay. And now on the feather, what I could do is so boot select is on the end here. The end here, that's where boot select is, next to a stem and QT port. So what you can do is you can hold that down and then hit the reset button. And that will get you into the bootloader. So we can see the RPI RP2 just pulled up. And let's actually just go to the downloads page, but we want the feather version. So let's just do RP2040, and we'll just use this version. Hopefully it works. Downloads. Adafruit. Feather. Too many downloads. RP2040 beta 2. There we go. Copy that over. Does this cable have data? Yes, I think so. But that is something I've totally forgotten as well. I have USB cables that allow you to turn the data lines off. Where in memory does the PIO code go? The PIO code goes into a dedicated instruction memory on the PIO peripheral itself. And there's 32 slots for 16-bit instructions. And that memory is shared between 4 state machines and an individual PIO. And you cannot read it, I don't think. Yeah, and if folks, Lady Ada is in the Discord chat, so if you want to join that, you can go to adafru.it/discord to chat there. I copied it over, but I got the drive back, which is not good. Did I not copy it? Copy here. I probably forgot. Luke says you can read by writing PC and then reading the SM instruction register. Right. Right. So you can read the currently executing instruction. So yeah. It's 64 bytes. You can always remember what you write to it. Totally. Oh, and it erased everything because I changed how much space we save for CircuitPython right at the last minute. So that's why I have a new folder here. Luckily, if I just pull up my editor, we'll see that I can just save this again. Oh, it's CircuitPy1 now. And just save as. Replace. And I'll also need the assembler library, which I just pushed to GitHub, but I think I have in home, repos, drivers, PIO ASM. Copy that over too. All right. Let's see. Are we on ACM2 now? Looks like it. Yep, and we're all updated. So let's simplify this frequency and just say, like, we just want to do 800 kilohertz. Hopefully my code works. And let's capture it again. Okay, so if we look here, we can see our frequency is 200 kilohertz with the width of 400 kilohertz. So let's take a look at our code. Let's get into the assembly. So what the squarewave here has is we set pinders, and then we have this program that sets the pins to high. So pins is a generic broad thing. And the way that we told it what pins means is that when you're using the set instruction, the first set pin is board.d13. And what you could do is you can actually address, so the way that you define pins is you say what start pin you want and how many pins not in addition, but total you want. So count. And count defaults to 1. So that's why I haven't provided it here. If we want to see, there's a lot of options. If you want to see all of the options, the read the docs should be up to date now. So if you go to circuitpython.readthedocs.io/en/latest, make sure it's latest. And exactly, Gareth says that's why you wanted 8 in a row. Exactly. So by having that side of the feather, or it's not all on one side of the feather, there's 7 on one side and then the 8th pin is on the other side, but they're all next to each other. What you can do is then you can use all 8 all at once from a state machine. because it requires them to be consecutive. Okay, so if we go to the design, not the design guide, core modules, and I think there should be, yep, an Rp2pio. And there's this big long list of parameters that you can give it. So you could see a pattern here. So program, you have to provide, frequency you must provide. You have the option of giving it an init, which is another program. But the way that it works is you can override the instruction by just writing to a register. And so the way that init works is that it starts your program and then writes kind of concurrently with that, which is a little weird and kind of a gotcha. So be aware of that. And then you can see a pattern here. First out pin count. First in pin count. So that's for out, in, set, and side set. And then there's also this exclusive pin use. This is just a helpful thing to say, like, I'm the only state machine that's going to use this or not. Kyle Ballard asks, what is the best resource for understanding wiring on microcontrollers? I had 20 years of development experience, but 0 with electricity. I think the wiring part is like what you're going to get with a lot of tutorials, like telling you how to hook up an LED. So I would just look for Adafruit. You just go to learn.adafruit.com. And there's lots of like beginner guides that will talk about the wiring side. And remember, like, this Rp2040 is a microcontroller. So even if you're following a guide that doesn't have that specific chip, a lot of it's going to apply across. So yeah, I'd recommend just like go to learn.adafruit.com if you want to learn the stuff off the chip, the hardware side. I'm totally with you. Like I'm a software developer by training. I learned all of the, I'm a computer engineer by training. So I did have 2 electrical engineering classes, but a lot of the EE stuff I learned. So you can learn it. And Adafruit was one of the places I learned it before I worked for them. Okay, so let's iterate on this PIO example and just see how the waveform changes. You're welcome, Kyle. That's what deep dives are for. Okay, so one thing we can do is, well, we should delete this comment because it's wrong. So one thing that's weird is that we're not seeing 800 kilohertz out. So let's see if we can change this program so that it is 800 kilohertz. First, let's simplify it by removing this set pin direction. So what this allows you to do is it tells you it's an output. And in fact, we're doing that with init instead. So we could just delete that and we'll get the same thing to happen. So if I just run this again, we should see the same, right? We're still at 400 kilohertz or so. So let's count cycles on this. And this is the reason the PIO is really interesting, is it's designed to be cycle accurate. So the first instruction, so this is again is a label. So when you do jump again, it will go back to where that is. Hi, Alvaro. So set pins 1, and then in brackets here is the delay. So what this will do is this instruction, this line will take 2 cycles. It will take 1 for set pins 1, and it will take 1 for the delay. So that's 2 cycles. And then there is set pins 0, which takes 1 cycle. And then there's jump to the top again, and that takes 1 cycle too. So there's 4 total clock cycles in this loop that we're running. So this frequency is how long it takes for 1 clock cycle. So if we wanted to actually get a square wave that was 800 kilohertz, we'd multiply this by 4. So let's just do that. Let's save. And I should show that the REPL is, you can see here. So what it's saying is the real frequency. So the 800 kilohertz is 3.2 megahertz. So if we just do our logic pro again, we can see it's a lot narrower. But it's still not, it's 1.6 megahertz. And my settings turned up? Yeah, my settings are turned up. All right, well, let's keep playing around with this. I had this working before. What I'm expecting to see is 3.2 megahertz. So it's still divided by 2, which could be a bug as well. But let's do the fastest thing. Can you do the one twice as longer than the, yes. So what we could do here is we can actually just say like, okay, let's make this delay of 3 and see what it looks like. So now what we can see is that this top one is 1.2848 microseconds, and the other one is 6.24 nanoseconds. So it's twice as long here as there. Oh, it was. And if we wanted to make, now that this loop takes 6 and not 4, we could adjust it here. So do that. And stop. And yeah, we can see the frequency there is 800 or so. So yeah, I think our math is right. Gareth says, love how the try commits test cycle is like 2 seconds. 100%. And this is the thing with CircuitPython, is that CircuitPython, its goal is to make code really quick to run and iterate on. And so it, like, CircuitPython just detects when the file is saved and tries to rerun it. Bye, Mr. Certainly. Enjoy dinner. It sounds delicious. Okay, so let's get this down to the minimal square wave, because this will allow us to talk about something else. So right now we have 6 instructions, there are 6 cycles. If we drop this to 1, that gets us back down to our 4. But the state machine has a feature called wrap. And what it allows you to do is it allows you to set the bounds of the program that the state machine is running. And so if so the program counter counts up, and when it hits that bounds, it will automatically go back to the part you told it to start with. But by default, CircuitPython will just set those bounds to the bytes of the program itself. Good night, Dave. Thanks for hanging out. Okay, so what we can do is we don't actually need this jump, because using wrap, in this case automatically, will all just go between the 2 instructions. So what we can do here is we can do that. And because we have this one delay, so David says, I don't have a scope like that. Is it possible to do a low-cost scope with Clue or other board with a screen? You know what? The Rp2040 is like the perfect thing to make a low-cost logic analyzer out of. We haven't done it yet, but it's like the perfect thing. And the reason it's the perfect thing is you could write a PIO program, and they've done this. It's in the examples, where it just you set the clock to 125 megahertz, and it reads the state of the pins in at 125 megahertz. Yeah, so this is the perfect example. We should put something together. So yeah, I actually the PIO and this is, you know, one of the reasons I was excited about this chip is that yeah, and you could even do triggering and stuff. So you could do things like, some of you may not have known, but I tried to make a CircuitPython powered Game Boy cart. And the Game Boy cart that I've designed is not reliable. It like will run for like a minute, and then like artifacts start happening, and like it stops working. And so what I really needed is like a thing to debug why that was not working. And like the PIO on the Rp2040 is like the perfect thing to be able to like sit on the Game Boy bus and just log what's happening until like nothing's happening. And then I could just see what happens before that. And that's a SAMD51 and the Game Boy cart. And I had so much trouble getting the SAMD51 to be like in sync with the bus of the Game Boy, because the Game Boy is clocking data in and out. And so I like fully appreciate like not having something at the very edge that can do things like this. So the PIO is really cool. And I think, you know, CircuitPython is not super real time. But it orchestrates things that are. So PIO is a good example of that, but also like that's why I'm thinking about the second core not running Python, is because you could use it for a like tight, just like we're writing like tight PIO assembly, we could write tight Cortex M0 assembly on the second core instead. Alice Tries says, ooh, it's tempting to write a basic Pico logic analyzer support into SIGROC. If you want to help me with that, I have a project called Tinlylogic Friend that I want to come up with a standard protocol that SIGROC supports that all of these micros could run on or use to talk with it. So yeah, if you want to help me with that, please. I just haven't had the time. But I would love to make just a generic tiny USB based logic analyzer that could run on like all of this class of hardware. Like obviously I think the Pico would be able to like do higher sample rate, but you could do it on SAMD21 and stuff too. And Patrick, thanks for putting the repo in there. Skyrim support would be awesome. Yeah. Now I can't think of the SIGROC. Yeah, I totally feel ya. Okay, let's get this down. So I talked about auto wrap. And so if we just delete the delay and hit save, what we should be doing is kind of like going full speed. So let's do, now it's 800 kilohertz times 2. And let's see what we're getting here. So now we're getting 800 kilohertz frequency with top and bottom. So like we're there. 800 kilohertz is just like NeoPixel speed. That's why I'm using it. So yeah, that's really neat. And somebody asked how fast it could go. So let's see how fast it could go. So let's do 125 and then 123, 123. So that's core speed. And oh, I left the 8 there. I think it should have overflow converting long int to machine word. That's not the right exception message for it being too large. That's not a friendly error message. Okay. It didn't crash though, which is good. Okay, so we're going full speed. Let's make sure the logic analyzer is full speed, which it is. David says, do you have a D assembler? No, we don't. But it shouldn't be too hard to write, actually. Yeah, Toddbot says at least there's an error message. Okay, so this is full speed. And it's important to note that I'm outputting a signal that's 125 megahertz and I'm reading it with a 500 megahertz signal. So I believe that this would be equal on, equal off, but because I'm like reading it not fast enough to see that. Anyway, I think it's right. I don't have any extra delays or anything. So yeah, I think that's right. Although it's like 10 and 6. Yeah, Luke says PIO output will be 50-50 or something. So sampling artifact is the right term. All right, 330. Okay, so should I show NeoPixel? So let's just do NeoPixel, but we'll do it on... so let's talk about how we do NeoPixel in 3 instructions. And this is a modified version from what the example code is in the Pico SDK. Okay, so let's change this back to 8 times 6. Not that slow. 800, 1, 2, 3. Right. They support low IO voltages. It's the Salier's fault. It doesn't look perfect. Okay. But now I named it program, which is like super unhelpful. Oh, and we have to write something to it, and it's side set. Wait, let's just pull up the library. I think I might have it. Here we go. Okay, so let's see if my example that I committed works. So let's just copy, paste, save. Okay, it's going. Did I miss it? I got something. I thought. Oh no. Oh, it's live. It's waiting. Oh, I'm on the wrong pin. There we go. So David says CircuitPython will use the PIO and the user will want to use the PIO. How do you deal with that? Right. So CircuitPython wants to use one state machine. Oh, FedEx 1K. Are these for sale in the USA yet? The board I'm using, this Feather Rp2040, is not. We're waiting to get more chips from Raspberry Pi, but you can buy a chip that's board that's running the same chip called the Raspberry Pi Pico. They are for sale right now, and they just put more in stock at Adafruit.com. So check that out. They'll ship out on Monday because it's late on Friday there. But yeah, they're in stock. And if it's not in stock, they put them in stock in batches. So if it says like add my email, just add your email and they'll email you when they set them more in stock. Okay, so woohoo, yes. So here's our NeoPixel output. We can see that zeros are 33% duty cycle and ones are 66. So let's talk over how that happens. So did I answer the question about how we allocate it? So basically what we do is CircuitPython manages state machines. It doesn't, it presents you state machines. It doesn't allow you to do PIOs. I have an idea. So there are cases where you want multiple state machines on the same PIO. And so I have an idea of how I'll allow you to do that. I haven't figured out all the cases. So like most things in CircuitPython, what I'm doing with the API is I'm starting from the thing I want to do. And as I want to do more things, I will expand the API. It can be an API design trap to try to support everything up front. And we can benefit from the fact that Micropython does. So if somebody needs something that we don't support, they can use Micropython in the interim. Of course, it's open source, so you're always welcome to hack on CircuitPython as well. But yeah, so CircuitPython, what it's doing is it's automatically assigning state machines to you when you ask for one. So what my plan is so you give it a program, it sees how long it is and figures out, can it fit in this PIO? If not, put it in the other one. And then it also there's tons of logic around pin in use checking that I had to add. If you don't want exclusive pin use, what it will do is it will say, is that pin in use by a PIO that I'm trying to put you on? And if so, then it'll work. Otherwise it won't. And when I was first working on this, I had a lot of issues. I just didn't set things right. So there's a lot of checking as well of if your program has an out 2 pins, it will make sure that you provided an out pin, for example. So there's a lot of, CircuitPython tries to have a lot of guardrails so that if you're if you mismatch what your program does with the pins that you provide, it should raise an exception and say hey, you need this or that. So that's the goal, but it's a lot of logic and it's probably not all correct. But that's the goal of how PIO works, is that you say, I want a state machine and here's the constraints about what this state machine needs. And then we'll pick the one that works for you. So that we can share user use of state machines with internal uses of CircuitPython state machines. So it actually, when we do NeoPixel right now, we actually like pick a state machine every time we do a transmit, which is a little weird, but it works. So that's good. Okay, so let's go over this, how this works. So we don't do anything with this program designation. It's just a name. Side set 1. So this is saying, I talked earlier about like how delay, the 5 bits of delay and side set are shared. What this does is it's telling the assembler like how many bits of side set am I using. I don't know if it's how many bits or how many pins. I don't know. It's probably bits, but I don't remember. If that just changes the way of like what a valid program would be. Okay, so you can also designate wrap target. So this is the start of your wrap area and the bottom of your wrap area. This could be useful if you have like initialization code you actually do want to run. But generally, like right now, I basically like it always wraps around everything. Gamma Game says, I'm looking forward to the Feather for LiPo support. Do you think it will eventually be a version with Wi-Fi and Bluetooth as well as a battery? I know the board is already cramped. I wouldn't expect us to produce a board that has it built in, but there is already an airlift Feather wing that should work with this. And it runs an ESP32, and like we have all the code to use a coprocessor like that. So I don't expect an onboard one, but the existing airlift stuff will work with this because it only requires a SPI connection. Okay, so let's take a look. We've got wrap targets around the outside, which I think the assembler actually just ignores. The assembler is a subset of the real one. So it's actually 4 instructions. So there's these 3 labels. There's bit loop, do 1, do 0. Those are just labels that don't count as instructions. And labels are like a way to like easily get a value rather than having to worry about what the number is. So the first thing you do is you do an out from, it's an out. So it's shifting out of the output shift register into the X register, the X scratch register. It is doing 1 bit, and then it's doing a side set to 0 and delaying 1 after that. These instructions are powerful. There's also one other thing to note is that if you can see here, there's this autopull, which means that out will automatically, if there's no more bytes to transmit, it will wait. So it will stall. So that delay could actually be more. And then the other thing it will do is it will automatically fill up. If there is data, it will automatically take that from the TX FIFO and put it in the output shift register. So yeah, that all happens here. And it means that if you haven't written any data to the FIFO, this is the instruction where it's stalled. Yeah, Alvaro says, cool ASM library would be nice to have something similar for the RISC-V chips coming soon, like the S3. It would also be cool for the second Cortex M0 in here, I think. Correct, yeah, and Bruce points out that the Arduino Nano RP2040 has a built-in Wi-Fi chip, which is probably running similar code to what the airlift is. Okay, so the first instruction is let me get in 1 bit from the output shift register. And then because like we're not transmitting like any sort of like the actual bits, so to speak, right? Like we're not writing directly to the pins. What we're doing instead is we're changing our behavior based on each bit. So The second instruction is a jump, and it's based on not x, which I think is basically like checking if x is 0 or not. So if it is 0, so we shift it in 1 bit. If it's 0, we do 0. And concurrently, so side number is concurrently at the same time. So if we're looking at our logic signal as low, and we're doing this jump, it goes high. And then we have a delay of an extra cycle. And then it goes to, if it's a 1, it goes here. Or if it's a 0, we go to do 0. So to do 0, we do nothing. We do a side set that drops it back down, and then we delay another cycle. If it wasn't 0, so this jump passed or failed, then what we do is we do this jump. There's no condition. See, there's nothing here. We just go to bit loop. But we side set 1, and we delay still. So what that means is that if you are a 1, you get here. So 2 cycles of 1 here, 2 cycles of 1 here. If you're a 0, you get 2 cycles of 1 here, 2 cycles of 0, and then you get at least 2 cycles back up at the top. Did that make sense? So that's, I guess let's go down here. So what do we need to do? What do we need to like set up the state machine with that program? So we do assembled, and we do a frequency of 800 kilohertz times 6. So 6 is the total number of cycles kind of in our loop. Yeah, it's a lot in 4 instructions. Exactly. So like everybody's like, oh, 32 instructions is not a lot. Like you can do a lot. And the concurrency also means that you have more like timing prowess, right? So 4 instructions, we initialize via a set. So this is just making sure that the pin is set to output. We say first set pin is D13, just because that's what we're listening to or like scoping. And then we also, so set, we don't actually use in our program, right? We're only providing that because we're using it in our init program. And then we also, pins can be used by the same thing, right? So side set pin is also D13. So we would be able to change it both in set and side set. Autopull we already talked about. And then this output shift register is interesting as well. Dexter says, is this microcode? I guess you could think of it as microcode. Like it's definitely like lowest level. Yeah, it's I think it's okay it's assembly, and unlike like assembly is the API that like the instructions talk to the processor with, and then in really complicated processors there's microcode, which Dexter is talking about, which is like further translation that the CPU does under the hood to make it run faster, which like Intel and Ryzen will do. But I don't think that there's that here. So like what you're doing in the state machine is like you put it in memory and it's reading that memory directly. There's no like intermediate between like what it executes and that. And it reminds me to say, like, I think this is actually, for somebody who wants to learn how to use computers, this is a great, like, wrap your head around the fact that computers are number machines. Like, I think it's really exciting that, like, as you're seeing here, we're providing a way for you to experiment with the very lowest level of, like, how computers work, but in these bounds of, like, CircuitPython and fast iteration and things like that. So I think this is a really cool chip to, like, okay, you want to get in the weeds, like, here's the guardrails, but here's how you get to the weeds while you're doing those guardrails. So yeah, I think that's really cool. So output shift right just means like whether when you take a bit or more multiple bits, like which way it goes. And that can change in this case, like which bit gets transmitted first. that impacts this. And CircuitPython will, so the FIFOs are always 32 bits. So if you write 8 bits to it, CircuitPython will automatically put it to the right or the left. Yeah, and Timon is pointing out that this is the gateway drug to get into FPGA development. Yeah, so I think this is like the lowest level you can get with an ASIC, meaning like an application-specific integrated circuit, where you're thinking about timing, but that timing is within the context of clock cycles. If you're in FPGA land, you have to worry about like how long your wires are, and like that's a level even deeper. But that won't get you here. So David is saying, are we going to be able to program the other M0 in assembly language of CircuitPython? That's kind of what I'm thinking is actually more interesting than just doing threads. But somebody would have to write an assembler for Cortex M0. So you could write similar syntax and it would produce the bytes. I think that would be really neat. So like you're trying to do something in a PIO state machine, you can't do it. Figuring out how to be like, all right, I'll write, like 10 lines of assembler for the Cortex M0 and leave it off on its way. I think that would be really cool. Oh, Graham says I added ARM v6 support to micropython.native. Right, so you could translate MicroPython code to ARM v6. I'm not sure we have micropython.native enabled. I think we do. But we certainly don't have the assembler. The PIO ASM, the C version? Both. It has an assembler too. Okay. Interesting. You should email me links to that. We'll see. Just-in-time compilation on a microcontroller. It's the future. I agree. Oh, and microdev's pointing out that this actually came up. This is something I couldn't talk about, but microdev was talking about because the ESP32S2 has a RISC-V core for the ultra-low power processor. So the way that we manage another processor from CircuitPython is potentially something we could apply to all like these other cases where we have a separate thing as well. Gamma Game says, being forced to write assembly in university made me learn more about how computers work than most other classes. It also Zachtronics games much easier to understand. Yeah. Right. So it's cool. You'd be able to Ask Patrick says, is this a standard assembler or is it specific to the RP2040? It's specific. Yeah. It is not. Yeah, it's a custom instruction set architecture. ISA for short. It's only 9 instructions, really 8. David G says, can I skip the assembler and directly provide the hex value? You can, yeah, so this, like, if we just change this to print assembled and find my terminal, like, it just is, it's an array, so it's just buffers. So yeah, you can just provide that stuff if you want. Yeah, and like I said, and as Luke's pointing out, like the SDK docs are really, really good. So if you want to know more about it, the example abstracts stuff a little bit more. It allows you to like have a variable named T whatever, and then uses that in delay. But this PIO assembler that I wrote doesn't do that yet. It doesn't do any of the expression stuff. Again, like I'm trying to like start with a very minimal and go from there. Okay, and I never covered this actually, but the question was how do I actually get the bytes to the state machine? So the way that we have it right now is you just say state machine.write, and that will transmit, in this case, like 3 bytes, one after another. It uses DMA to do it, but it will block until it's done. I actually had a bug where it wasn't actually blocking until it's done, so I actually was turning the PIO off too quickly. So I actually had to figure out how to not only do I have to figure out when the FIFO is empty, but I actually have to figure out when the output shift register is empty as well, before I could turn it off. DCD asks, earlier I asked about getting exactly 800 kilohertz. Would you have to calibrate the frequency into the state machine instead of the 800,000? It should be really close. The accuracy is going to be... yeah, Luke says, oh, that was the TX stall thing. Yes, it was. To get exactly... the quality of the clock, of the timing of the state machine is going to depend on the quality of the input clock signal, which is like a crystal on the board. And then I don't know if the PLL, the thing that multiplies that to faster, probably has some wiggle room as well. But remember, I'm sampling, I may not be sampling it perfectly well. There's some timing related to when I'm reading these samples too. So it's 801 kilohertz is super close. NeoPixels are not that specific, so it's well within the range of what they expect. So David asks, the Rp2040 will take a week to get here. Can I use that library on another CircuitPython board, just the assembler library? You can use the assembler library in CPython. It's just doing a parse text, convert to bytes sort of thing. It's not specific at all. Let me click through all my windows. So if you want to see it, you could do the GitHub Adafruit. I'm going to start to wrap up, but if folks have questions, put them in the chat now, and I'll get to them. So it should be available. This PIO ASM should be in the should be available in the bundle as well. I got it in last night. Question for Luke. How are you planning on handling IP for the PIO? Closed, licensable, open architecture, open source? Whether people can re-implement something that works with the same ISA. So this is so for all of you who have not understood what RISC-V is, RISC-V is very similar to this. It is an instruction set architecture, and ARM and x86 are famous for you can't implement something that implements this thing. It's custom to us as well. And so that's why RISC-V was created. RISC-V was saying we're going to agree on the instructions that we give to the CPU. The implementations, they have some open source implementations of it, but those are not necessarily they don't have to be. Right, you can have closed source RISC-V chips. RISC-V is all about that API boundary, which is the instruction set architecture. And so that's a question for the Raspberry Pi Foundation folks, is whether they plan on keeping it the instruction set architecture, or even how it works, closed. I imagine that the best you'll get is the ISA is free, but I don't know. That's a question for them, and I don't know. That's not on me. But yeah, so if we just look at this PIO ASM thing, you can see I just have some this is the source destination thing. So it's how we map to what the value for the bits is. It's just a very straight, 167 lines of my terrible Python. So it splits the program. It figures out where all the labels are. It takes out some of the defines. And then basically it takes the instruction, it does delay and side set in a uniform way. And then, yeah, so that's delay and side set here. And then just based on the instruction, like start with a 16-bit value and then or different values into that. Which is, if we go back to the data sheet, exactly what this encoding thing is. So I was just looking at this and I'd say, okay, I'm going to do a jump. I parse a jump, and then the delay side set stuff is the same, and then putting in the other bits here. How novel is it? Is it patentable? That's a great question. I'm not a lawyer. I've seen like the BeagleBone PRUs and the FlexIO on the IMXs are similar as well. Yeah. Everybody thinks it should be open, I think, but I don't know the legalese around it. I do know that like ARM and stuff is right. Chris Ward says, what does this example do? This is just a small bit of what is required to control NeoPixels, right? So those 3 bytes you write are setting a color, selecting a pixel. They are color values. So the way that NeoPixel works is it's a big long chain, and there's you send 3 values, and the first pixel grabs it, and then any other values it gets, it just forwards on to the next one. So the way that you address it is just like when you refresh NeoPixels, you have to provide, like you could theoretically do like the start of a chain, but you have to like provide between the first one and the nth one that you want to update. You have to provide pixel values for all of those. So there's no like addressing in that way. Yeah, the color loop is constant. What you're seeing it change here is actually like CircuitPython telling me it's done. Oh yeah. Command says I took a good look at FlexIO yesterday because of this. It's so much less than PIO. I think PIO is what they wanted it to be, honest. Yeah. I've never done a lot of FlexIO, so I couldn't say, but the PIO is really neat. So yeah, so this is basically the timing sensitive bit of NeoPixel. It's just transmitting the individual pulses that indicate all the bits. That's the thing that's usually hard. So it's like GRB or something, like red, green, blue. I could make this twice as long, but you wouldn't see anything because I only have 1 NeoPixel here right now. It would have to be connected to a second one. Right, the assembler language, the assembler library is not. I mean, you're gonna get bits out. They're not gonna be useful, because to be useful, you have to hand them to a state machine. But there's no reason you can't run this bit on anything. I just built a Raspberry Pi tank and it's simple. Yeah, I think, let's see, is there anything I want to cover? It would be nice if this controlled the stuff instead of like an Arduino. I don't know what you mean. I fully, like, if I had to guess, I would expect like the Raspberry Pi 5 or whatever they release next is going to have one of these on board to manage all the real-time stuff, right? Like this microcontroller makes so much sense into comparison. It makes so much sense compared to what a Raspberry Pi can do, because a Raspberry Pi is like meant to compute a lot of stuff. It's not meant to be like very responsive to the outside world. So yeah, and it looks like the Picos with headers are still in stock. So if you haven't gotten one yet, you can grab them at Adafruit.com. Yeah, Ryan G says, can the PIOs do DMA? Yes, they can. So each of the FIFOs has a DMA request line. so you can do it. It can say like, hey, DMA, I need more, or I have more for each way. And the memories, the docs are really good. So the memory system is described in system functions. Yeah, so here. This is cool. Core 0, Core 1, system DMA, right? And then you have 16K ROM. You have your 4 big SRAMs for 256. And then you have 2 smaller SRAMs, 4 and 5. And the reason that those are interesting, and the reason that I think this chip is really cool, I mean, it's well documented, which is good, but it's also important to know that each of these SRAM blocks can be read and written at the same time. Like there are limited resources outside of a CPU as well. And I think that's really cool to know that. So they go into details about like how DMA decides which thing it's going to do. Seville asks, can the board show up as a keyboard connected to a PC? Yes, it can. A lot of CircuitPython boards can, and this one can too. It's known as HID, Human Interface Device. And I'm surprised, I guess I'm not on my Mac, but when I plug a new board in on my Mac, it will say like, hey, you have a keyboard. So it is actually showing up as a keyboard right now. You'll have to program it to do that. Seville says, what is the state of GUI development in CircuitPython? Is there a framework or a library for GUI development? Foamy Guy and TG Techie have been doing a lot of work on the framework side. The DisplayIO side hasn't changed a whole lot. But I think it's well positioned to be able to build widgets and stuff like that. So it's getting there. I wouldn't say it's comparable with a little VGL because they've done a ton of work. It's all C. But it's getting there. And I should also point out that because we have SPI implemented and I2C, DisplayIO is enabled on the RP2040 already. You won't be able to do parallel buses yet, but anything that uses like 4-wire or I2C should work on the display side on the RP2040. So e-inks, OLEDs, LCDs should all work. Gamma Game says, so it'd also be able to show up as a controller. That might be interesting for making something ridiculous to play Dark Souls with. Yeah, definitely. It shows up as a controller as well. And I think there are examples. It shows up as a standard, like it's called gamepad in HID terms. And so it's like a standard, like 2 joystick, 4 button sort of layout that it does by default. And somebody points out you could script it to play as well. You totally could. Yeah, so, one of the strengths of CircuitPython is that it's USB stuff. So it shows up as a drive for your code to edit. It uses a serial link to show you the errors. But it also shows up as a mouse, keyboard, gamepad. And then it has MIDI as well. So it can do MIDI control for like playing music. David says, do you have a checklist and priority for the features you want to enable when you have a new MCU on a new board? I don't. I don't. If you want to see what's coming for the RP2040, you can take a look at the issues list, and there's a label for the RP2 now. So that will cover that. Generally, there's with a new port, like getting USB to show up is hard. In order to get Flash working, like get the CircuitPython. So if USB is working, you can get serial communications. So that's the very first thing. Second thing is you get Flash reading and writing, so you can write a code.py. And then like once that's there, it's kind of your like a bit of a like choose your own adventure in terms of like digital IO is one of the first ones you want to do. Bus IO, because so many of the libraries use bus IO. NeoPixel is nice for like the status NeoPixels. So it's once you get USB going, it's kind of like a what's more important. But yeah, it wasn't super bad. Wasn't super bad. I have one of the HDMI adapter boards for a 5-inch display from Adafruit. I'm hoping to create a GUI for a project I'm working on, a candidate for DisplayIO. I don't think so, because we don't. The HDMI adapter boards usually take RGB24 in, and at the moment we aren't able to produce that from DisplayIO. But if you really want HDMI, the real thing you should do is I want to do bare metal on a real Raspberry Pi, so that a Raspberry Pi would show up as a CircuitPy drive, but be able to output, like, if you do it on a Pi 4 or you do it on a Pi 4 compute module, like, then you can have dual 4K screens from DisplayIO, which would be ridiculous, but also so awesome. David says you could forget rotary IO if nobody complains. Yeah, I mean, there's a bit of a, like, if nobody complains, why implement it? I think this chip is going to be popular enough that you will see us add all of the things. But rotary IO is definitely further down on the list. Like, I don't have, like, UART isn't implemented yet. So if like, UART is probably something I'll do next week, and audio PWM-IO would probably be cool too. Graham says you can't sell Luke short on his PIO-based dual-screen DVI. I mean, if he wants to add it so that it's on the second core, that sounds awesome to me. Okay, Gareth says, last question. With Micropython being the official system, your thoughts on how CircuitPython should be defined? I've thought a lot about this. I would love to see, CircuitPython be mentioned as much as Micropython's being mentioned. But at the same time, I'm very happy that we don't have I'm very happy to evolve APIs. And that's really hard to do if you have a book. So I'm very happy that, like, none of the CircuitPython stuff is in a book. And it didn't need to be done prior to launch. Like, we can evolve it and we can get a feel for how people are going to use things. So yeah, it's kind of it's mixed feelings for me. I would love to see it right alongside Micropython. But at the same time, I think, I want to get the word out. Like, I think it is the best experience, because you plug it in, you get a CircuitPy drive, and you can edit the code on it. So try it, tell your friends. We have written up a comparison. So I think CircuitPython is easier than Micropython, especially on the Rp2040, because the Rp2040 Micropython doesn't show up as a drive. You have to use it with Thani. It's kind of what they expect, or something else to transmit the files over. So I think CircuitPython is definitely easier to use, but Micropython has the more advanced stuff covered that frankly isn't a priority for us. So if you do want to run Python on 2 cores, if you do want interrupts into Python, if you do want all the features of the PIO, Micropython is a better choice, because it is comprehensive. But besides that, and for the most of the things that you want to do, CircuitPython is going to cover you. And as we find uses for PIO that we can't do now, we will add things. One thing that CircuitPython's really has going for it is we're not static. We're going to continue to work on this. We're open source. We take pull requests. We have that stuff down. Gamma Games asks, will there be an extension for VS Code to use CircuitPython? There already is one. And in fact, one thing that CircuitPython does really well is all of our APIs that are implemented in C are still documented in Python stubs, which means editors like VS Code can read those Python stubs and do auto-completion for you. So yeah, I think there's a lot to argue there. Gareth says, I agree, full features are less important than good docs, community, and responsiveness. And I should say, there's nothing stopping you from trying CircuitPython and Micropython to figure out which one you like. Just be aware that the file systems are different, so back up your code before you do that. But yeah, try CircuitPython. That's the message I want people to get away with. Oh, it's just so many good questions. Okay, let's. How do you feel about it being used in education, like as a college EE course before intro embedded systems? That way, students can get used to concepts like I2C protocols before worrying about learning about the embedded level. I don't know what you mean by embedded. Do you mean like concurrency and RTOS stuff? David says, is this the first board where we can really compare between MicroPython and CircuitPython? Yeah, I think to some degree. Like there are chips that run both, but like this is kind of the first one where we're both really trying to fully implement it. Like MicroPython has SAMD support, but it's like very, very limited. And CircuitPython has ESP32S2 support, but MicroPython has ESP support. Oh, Lady Ada points out the STM32F405 feather runs both pretty well. So yeah, maybe not the first one, but yeah, another good comparison. Keith, I think this is a great first board. It's inexpensive. It allows you to get into these like cycle accurate, what is a state machine, I'm crunching numbers sort of scenario, which I think is really cool. Command says, does embedded mean fighting with poorly named registered on poorly documented chips? Well, this one does not apply to that. This one is so well documented, it's a breath of fresh air. Alice Tries points out like Rp2040 looks like the perfect chip for CircuitPython, all reflashable over USB, 100%, and you can't mess up the bootloader either. Like the bootloader's burned in, like you'll never not be able to get it. I would love one caveat for those of you who use CircuitPython on other boards. Right now, double tap to reset does not work. Reset into the bootloader. It might in the future if you already have CircuitPython enabled, but there's no way to guarantee that that works. So boot select is going to be a thing for a while. Lucas says, I'm curious if CircuitPython will get the ability to enter REPL programmatically with predefined variables, like run REPL on the BlackBerry keyboard feather. I haven't seen how that works. Generally, versus MicroPython, CircuitPython tries to clear the state before running code again. And so all the state is cleared entering the REPL. So I think that's what you're talking about. Wish we had these when we hacked Xboxes. I know, right? There's a lot of like retro computing stuff I want to do, and this is a really good, like, dealing with a single megahertz sort of signal like should be totally doable in this. Oh, the other thing, like MicroPython versus CircuitPython, is like we've been very strict about having a common API across all of our boards in CircuitPython, which means that all of our libraries generally work. If like a board can't do something, the module for it won't be available. Akusa Tuna said, but will it fit in a Game Boy? Probably. Oh yeah, I should drink water. I haven't been drinking a lot. I have a glass. I'm only halfway through it though, so you're right. I've been like, I'm so amped. Like, I was so excited about this chip. I think it's very cool. So command is saying in the docs they say you have to install the universe build chain. I just switched to my Linux box and you just need ARM GCC. I guess the universal build toolchain is only for debugging. So the GDB that they use is the multi one because of the 2 cores. Which I did do a little bit of when I was debugging it first. I wish there was more hours in the day to play with stuff. I feel ya. It's a very weird case for your hobby to be your work. And there is a BBC emulator that somebody put together too. Oh yeah, and you can't see me. Sorry. When I'm just answering questions, I should definitely have it on my face. Okay, let's wrap up. The cat is up in the window watching out, and it's actually kind of hot in here. My cat's got a kick out of the Sphero, which I have here too. Let's see, did I cover all these tabs? The magazine, the blog post, getting started, feather. Yeah, so if you do want it, let's see. The Pico itself is out of stock, but the in-stock, now you can't see my screen. Adafruit.com/product/4883 has the Pico with loose headers included. So if you haven't picked one up yet, check that out. Thank you to DCD. I imagine that has been doing time codes. I definitely did not. So thank you for that. Adafruit.com, support Adafruit, which supports me. They pay me to do all this stuff. As folks are saying, if you haven't subscribed to Adafruit yet, please do. There's lots of great technical content on there. Click the bell if you want to see when we go live, I guess. This has been a deep dive. We dove deep, which was awesome and exactly what we're here for. If you have more questions, deep dives happen Fridays at 2 p.m. Pacific. So, 2 hours previous from now. If you have questions about the RP2040, you can find me and a lot of others on the Adafruit Discord server, which is around all week, not just during this time. So if you want to ask about CircuitPython, ask about the RP2040, that's where you can find me. You can join the Adafruit Discord server by going to adafru.it/discord. Let me type that out and copy it around. Although I think folks are in the chat and in that. I think you should. I think it's safe to assume that next week will also be about the RP2040. So if you don't ask questions in the meantime, you can find me here next week on that, and hopefully UART will be done. Maybe the audio PWM stuff too. We don't have random implemented. I don't think there's a random number generator. So we'll have to figure that out. But yeah, thank you all. It's been such a pleasure. And sorry that link doesn't actually. Pleasure to have you all talking about this exciting new chip from Raspberry Pi. If there's another new chip, well, I will have not worked on it. But super exciting. Congrats to the Raspberry Pi team for getting this out. I think it's going to be something we're using for a while. And Luke confirms there is a true random number generator, so I'll have to add support for that too. Until then, check out CircuitPython on the Pico. It's not official, but Adafruit is supporting me to support it, so expect it to be getting better and better over time. And with that, the cat's watching out the window, so I'll say goodbye and chat with you on Discord and then stream next week.